Welcome back to our Unit 7 notes. This is the second video, so if you're watching it in error, you'll want to go back and watch the first one before you come to this. You've already started making on your own paper the notes. We are going to switch to a very different style of notes now. So I'd really recommend you find some white printer paper and hold it horizontally, long ways. And after doing so, fold it into 4 sections. So fold it in half again, open it up, and then across the top, draw a little space bar there. We're going to title each of these 4 columns, because what we're really going to set up for is really like a T-chart, but 4 pieces. It's going to allow us, though, to compare and contrast the types of bonds. So it's going to function very much like a T-chart. Across the top here, these 4 boxes way up here at the top, those are going to be these titles. The one on the far left should say topic. The one next to it should say ionic, as in ionic bonding. The one after that would be covalent, as in covalent bonding. And then on the far right, we're going to have metallic, as in metallic bonding. So these are the 4 titles that go across the top here that you drew. I hope that makes sense. Okay, so fold your paper, draw or write in these words and then draw a line across or something like that. These are your notes again, so you don't need to necessarily worry about using a ruler or a straight edge, but that's up to you. You can pause the video and do that. And then once you're set up with this, then restart the video and start filling it in. Okay. Our first topic is composition of the bond. So in that the first space right below that far left column, you write in composition of the bond in the column. That's what goes in that first column on the far left. Composition of the bond. Those words literally right there. Okay. Now you move to the ionic column. Okay. And so what is the composition of an ionic bond? Well, the composition, what makes an ionic bond is ions, cations and anions. So an ionic compound is comprised of positive and negative ions. Okay. So you need those positives and negative ions, those cations and anions, and they're going to be electrostatically, isn't that fun, electrostatically attracted. And nature will work them out in the right ratio so that they always total 0 when you add up the positives and negatives. So some examples. Sodium's a +1, chlorine's a -1, 1 of each. Okay, but sodium's a +2, +1, oxygen's a -2. So it would take 2 sodiums to join with 1 oxygen. And nature has, whenever nature even has the tiniest bit of sodium and the tiniest bit of oxygen around, it's got like gazillions of atoms of each of those. So it can work it out just fine. So an ionic bond is made up of positive and negative ions that are electrostatically attracted and total up to 0 in the end, 0 charge overall. Okay, so here's a really nice picture of how this would work for sodium and chlorine. Okay, most ionic compounds end up what we call a crystalline solid. That is, they not just make a solid, they make a solid that has a particular repeating geometric shape, a crystal. And so it really is, a crystal is a 3-dimensional network of positive and negative ions. So here's my neutral sodium, here's my neutral chlorine. They get close enough to react and an electron is transferred. And now I have a cation, sodium's the cation, and I have an anion, chlorine's the anion, and they're going to ionically stick together into this 3-dimensional repeating pattern, and that is a crystalline solid. In this case, it's table salt. And you can see, I want to kind of point this out, what happens, and this is always what happens, like the positive is surrounded by negatives on all sides. The negatives are surrounded by positives on all sides. That positive is surrounded by negative on all sides. And so really for every 1 atom of sodium, it's surrounded on the top and bottom, the left and right, the front and the back by chlorine. And then each of those chlorines are surrounded on the top and bottom and left and right and front and back by a sodium. And then the pattern repeats. And that's what makes these crystals. So I don't know if you've ever seen sodium chloride table salt crystals underneath a microscope, or even a good magnifying glass is all you really need. It always forms shapes that are roughly flat sides and 90-degree corners, because I mean, look at what we got going on here. We have something that really makes very nice cubic shapes. That is characteristic for sodium chloride, and that is the ionic solid going on there. And it's not something that just happens randomly. If you look at sugar under the same magnifying glass, it is not going to have that kind of shape to it. And of course, different ionic solids are going to have different shapes to it. Okay, so that was the ionic column in your notes. So let me, real fast, let me go back. In the very far left column, you wrote composition of the bond, and now in ionic, you have written down this about cations and anions forming a crystalline solid and being neutral, 0 overall. Okay. Now in the next column over, the one that at the top says covalent, you're going to write this stuff. Okay. A covalent bond, what's a covalent bond made? Whoa, that's not the button I meant to push. What's a covalent bond made up of? It's made up of sharing. So ionic bond was made up of a transfer to make ions that then stuck together. A covalent bond shares electrons, and it shares electrons in pairs. Electrons always are shared in pairs. Now we can transfer 1 electron or 2 electrons or 3 electrons. We'll get into more of that later when we actually look at the shapes and bonds and stuff. But with sharing, we always share in pairs. Okay. Now it's possible it's shared equally. We call that non-polar covalent. You should know that term by now. That is, both sides get the electrons roughly the equal amount of time, and so therefore there is no positive or negative side to the compound. And it's also possible they share unequally, and then it's polar covalent. And one end that gets the electrons more of the time is a little more negative, like the south pole of a magnet, and the other end that gets the electrons less of the time, it's a little more positive, like the north pole of a magnet. So we really are talking like poles of a magnet, a negative end and a positive end, or a south end and a north end. Okay. Again, the type of bonding between, is it non-polar covalent or polar covalent? It depends on the electronegativities. Okay. But I'll give you a big hint. If you look at like my A and B here, they look really equal. It is very possible that they would be even the same atom. So if it's the same atom, like say 2 hydrogen atoms together, well that's, hydrogen there and hydrogen there. That's got to share equally because they're the exact same atom. Okay. On the other hand, if they were different atoms like hydrogen and chlorine, those aren't even close to each other in the periodic table, and so they really probably have very different types of electronegativities. So the best way to prove it's non-polar covalent is to have exactly the same atom in the bond, one of each on each side. And if it's different atoms, there's a very good chance it's a non-polar covalent. So just give you some hints there.
Many atoms form covalent bonds. In covalent bonds, electrons are shared by both atoms. The first energy level in atoms can hold 2 electrons. By sharing electrons in a covalent bond, each hydrogen atom has a full outermost energy level. Water molecules are also held together with covalent bonds. Again, we see that covalent bonding gives each atom a full outermost energy level. The outermost energy level for hydrogen can hold 2 electrons. The outermost energy level for the oxygen can hold 8 electrons. In covalent bonds, the shared electrons move between the atoms that share them, forming a single electron cloud around both atoms.
Okay, so did you catch that? Sharing electrons, it's very much like merging the electron clouds together. The electron pair, can I not write here? Okay. Well, the electron pair that would be here around this hydrogen could migrate over here to this oxygen. And in theory, could also migrate around this hydrogen a little, and then back over here to this oxygen, and then back over here to this hydrogen. Now, in water, where is it more likely to be found? Well, oxygen, look at all these positives here, okay? Oxygen is way more electronegative than hydrogen, so it's very much more likely to be held around oxygen. If I took, say, 100 pictures of where those electrons were, I would probably see the electrons that are being shared around oxygen easily like 80% of the time. So oxygen's getting a little more negative. The hydrogen's a little more positive. I'm setting it up to be a polar covalent. It's just got a negative end, a positive end. It's like the poles of a magnet. So that's polar covalent. But again, the point of this video was for you to see how the electrons get shared as pairs. And so they can go around both types, both the atoms or all the atoms involved in the sharing. Okay, that was the covalent column. Now we should be on the far right, the metallic column. Under the metallic column, what you want to write down is this stuff. Okay, metallic bonding accounts for the properties of metals. I mean, very much everything. Okay, let me start with this. So my children come back from kindergarten, and they announce, "Hey, we did science day." And I say they because my daughter did the same thing when she was in kindergarten, and then like 6 years later with the same kindergarten teacher. I mean, what's the luck, right? They did the same thing, and they've both come home saying, "We did science today." And I'm like, "Okay, I'm curious, what science did you do today?" And they said, "Well, we did the Is It a Metal lab." I'm like, "Okay, so what did you use to determine if it was a metal?" And they said, "Well, we asked, is it shiny? And is it hard? And does it feel cold to the touch?" And they listed off all these characteristics that you go, yeah, those are like indicative of metals. Why are those particular set of characteristics seem to be common to all metals? Well, it is literally metallic bonding that gives metals the properties we expect from them. So, metallic bonding is highly mobile valence electrons. In fact, we have a fancy word for this, delocalized. Okay, because if you're local, you like stay nearby. Well, these are delocalized, so they go out. So again, this electron could like delocalize all the way around out here, kind of zoom around here, roam around, delocalized, okay? But we also, and I don't know why, I'm sorry, but this is used over and over again. It's not necessarily wrong, it's just another analogy for it. It's called a sea of electrons. You need to know that vocabulary as well. So not only do you need to know delocalized, meaning that it's highly movable valence electrons, you need to know sea of electrons. It's just the name of our model for metallic bonding. It is what it is. I didn't make the rules. They're the ones expected of you in this class in AP Chemistry, so you need to follow it. What are we referring to with sea of electrons? Well, pretend instead of nuclei, okay, that these are in fact jellyfish. So I'll just like draw some little tentacles coming out from the bottom of my jellyfish here. You get the idea. And I know you're just awed by my artistic ability going on here, right? Okay, so here's my jellyfish. Where do jellyfish live? They live in the sea. Okay, and the sea just happens to be with nuclei jellyfish. The sea happens to be negative electrons, like that one and that one and that one. So do the jellyfish get to claim any particular part of the sea that they're living in? No. The sea kind of moves back and forth and around, and waves go up and down and all that sort of thing, and the jellyfish is kind of there. And so, no, you can't say that this particular jellyfish owns this particular part of the sea. The sea is shared amongst them all. Same thing with the metals. The nuclei just kind of seem to stay there, usually in nice, neat little rows or something very similar to a nice, neat little row. And then the electrons just kind of move around, ebb and flow, back and forth around like the ocean water would around a bunch of jellyfish. Okay, so very highly movable valence electrons, because they all have a very low ionization energy. so they can't hold on to those valence electrons very tightly, so they're easy to move. We call it the sea of electrons model, and the fancy vocabulary word for highly movable valence electrons is they are delocalized electrons. So I'm sorry for you to memorize, but hopefully I've helped it make sense, and then it's like really less for you to memorize because it's more that you understand. All right, so that finishes the metallic bonding category. Now you want to draw a straight line across all four, just, without a ruler, just freehand a straight line across all four of those columns. And now we're ready for the second set across the columns. So topic 2, on the far left, you already wrote composition of the bond. Underneath that, I want you to write types of elements involved. So this is going to be horizontal row number 2, types of elements involved. I hope you're understanding how we're setting this up. Okay, so now we're in the ionic column of your notes, that, left side of the middle column. And the ionic bonds form between elements that have a very large difference in electronegativity. Now this is kind of like, this is a fact sort of thing. To get an ionic bond, we need elements that have a very large difference in their electronegativities. Well, how do we do that? Well, we really pretty much, this is a very good rule of thumb. We are going in, yes, I know what I'm saying when I say rule of thumb. If you don't know, that's all right. But it is a good rule of thumb to say it's going to take a metal and a non-metal to make an ionic bond. We need something. You're going to love my awesome artistic ability. Hey, look, it's the periodic table. Remember that fun stair-step line we got going on there? It takes something from so far away from each other that we need something from this side of the stair-step line bonding with something on this side of the stair-step line to get a difference big enough to be ionic. And this is a very good generalization. It really works well most of the time. Of course, we could officially go to the numbers I've asked you to memorize, and that is a difference greater than 1.7 in electronegativity values. But just in general, metal and non-metal is what is needed for an ionic bond. Why does it take that? Well, the metal is going to lose electrons. Okay, that makes it positive. And metals lose electrons easily because they have low electron affinity and low ionization energy. Okay, they do not hold on to those electrons tightly, and if you give them one, it's going to not release a lot of energy, and it won't take a lot of energy to remove it. So very, very easy for them to lose electrons. And I already mentioned that, but again, when I call you a metal, I'm calling you a loser. Okay, because metals will lose electrons. That makes them positive, by the way. That makes them cations because you're losing negative electrons. Now you need the other piece of that. You need a non-metal. The non-metals are going to gain electrons. You need a loser, you need a gainer, or it's not going to happen. Like the bond is not going to form. It's just going to sit there doing nothing. So you need a loser and you need a gainer, and it's going to be the non-metals that gain because they have high electronegativities. And I hope you see one of the key words all throughout this unit is the word electronegativity. It helps us predict so much when it comes to the type of bonding going on. Okay, so high electronegativity going on there. All right. Now we're still in the ionic category. I want to throw a few more thoughts in. Okay, it takes a metal and it takes a non-metal. And most ionic compounds are going to be crystalline solids. Okay, what you need to get is some of the vocabulary. Crystalline solid, I already showed you some pictures, is a three-dimensional network of positive and negative ions. Okay, well, if I have a bazillion positives and a bazillion negatives, all like three-dimensionally located around, in whatever shape it is, whether it be square or whatever, I don't want to have to write that down. I don't want to be like Na gazillion, Cl gazillion, okay? We'll reduce to the lowest whole number ratio. For an ionic compound, that lowest whole number ratio is what we call a formula unit. Okay, so please understand and use that vocabulary. A formula unit's the simplest or lowest whole number ratio of the ionic compound's formula. So when we write NaCl, that is one of each, by the way. We don't write ones. When we write that, we're not saying in truth that I have just one atom of sodium and just one atom of chlorine. What we are saying, what we're really writing, is that the ratio is a 1-to-1 ratio. And that's all we know. I don't know how many atoms of each, but it'll always be a 1-to-1 ratio. Okay. And why do they do this? Well, again, it lowers their potential, it minimizes their potential energy. Okay. We call the whole arrangement a crystal lattice. Okay. So this shape that I showed you a picture of earlier, we call that a crystal lattice. Maybe you've seen in like lawn and garden shows or stores, or even like your backyard or something. There's this thing called a lattice, which is usually like some wood strips going this way and wood strips going this way, and then you can plant some vines down here, and they use the lattice to climb up, and there's all sorts of decorative. You can do something like that, and then get kind of a fan out shape of your vines, and it looks oh so pretty when the roses. Okay, you get the idea. Okay, well, they named it kind of after that idea. So a crystal lattice is the solid shape that is formed when the ionic compound minimizes its potential energy. We call the ratio of the formula, we call that a formula unit. And here, you don't need to write a single bit of this down. You can pause and stare at it for a while if you'd like, that's just fine. But here's the possible crystal lattices shapes that we have. So there's several cubic shapes. By the way, sodium chloride is one of these. I want to say it's the face-centered, if I'm remembering correctly. It's been a while since I looked at it. Maybe it's body-centered. But anyway, there's some cubic shapes. There's some more like rectangular shapes or rhombic. There's some tetragonal shapes. There's some monoclinic shapes. And then we even have some hexagonal shapes and some rhombohedral shapes and some triclinic shapes. And so don't be like, oh, well, how do I get sodium chloride to go from this to this? Well, you can't. But remember how I gave the example of sodium needing 2 sodiums to every oxygen? Well, that combination is not going to make a shape like this. It would make one of these other shapes. So very much depending on the charges and the types of elements involved, you'll get different shapes. For instance, water makes a hexagonal shape. So here's like an O, here's an H, and here's an H. And then here's going to be another O and an H, and then there'd be another, well, let's say another H down here, and that sort of thing. And we can talk more about that later. But if you really want to know, how to get these other shapes, it means changing the elements up. The element's identity and charge are going to determine what crystal shape it actually makes. So you don't need to write any of these shapes down. They're not going to be tested over or anything like that. But if you're looking for an interesting project to, make something three-dimensional to hang on, say, a particular chemistry or something, these could be a great idea of where to start. Of course, you'd have to build it. You'd have to tell me what elements would make that. You'd have to tell me why. You should be able to, research and tell me all that. Okay, we're done in that ionic column, the left of the middle column. Now we're moving on to the right column, right of the middle, that is, anyway. Okay, covalent bonds, they form between elements that do not have a large electronegativity and difference. Okay, so ionic needed a big difference. They need to be on opposite sides of the stair-step line, metals and nonmetals. Covalent bonds are going to form between nonmetals. Period. Like 2 nonmetals, nonmetals and nonmetals, or 3 nonmetals, or 4 if it's all nonmetals, it's going to be covalently bonded. That's a very good generalization that works really well. So go with it. Now, I do want to point out it is certainly possible for covalent compounds to share more than one pair. And if it shares 2 pairs, we call that a double bond. And if it shares 3 pairs, we call that a triple bond. It doesn't go any higher than triple bond, all right? And to explain why, that's the next unit. Okay, we'll get to drawing them, we'll get to like building some models, and then you'll see it's just literally physically impossible for them to, yeah, I know I killed the English language and made a word there. It's impossible for it to form a quadruple bond. So single bond is one pair, and that's all we've been talking about. Now one pair of electrons, okay, two pairs of electrons being shared at the same time, 4 total electrons, that's a double bond, and then 6 total electrons is a triple bond. Okay, and again, it can share equally and then be nonpolar, and it can share unequally and be polar. So I hope you're catching the repeating vocabulary that's so very important through all of this. When it shares unequally, that is a polar bond, and I've already discussed how it sets up like positive and negative end like poles of a magnet. I want to introduce you to this thing called sigma. Sigma is what this Greek letter, I don't know what letter of the alphabet it like matches up with. It doesn't have to necessarily. Anyway, but sigma is the symbol we use to show a partial positive or partial negative. Not a full out positive or negative like it's a cation and anion. This is just a partial. This tells me the electrons in this bond, that line represents a shared pair. 2 electrons is what that line is, okay? Shared pair of electrons. This negative tells me it's going to be around the chlorine more of the time and maybe around the hydrogen a little bit. Okay, so I have a negative end, a sigma negative end, a partial negative end, and a sigma positive end, a partial positive end. Now, how do I know which end is going to be which? Well, I've already mentioned that. I hope you caught it earlier. If not, here's your second time, okay? It's really easy to know, okay? The more electronegative element wins. So chlorine being 3 compared to hydrogen's 2.1 means that chlorine's going to get the electrons more of the time. If it gets the electrons more of the time, that end of the molecule is going to be negative. And this is going to be important for us to know what we mean by a polar compound when we get near the end of the notes and we start discussing what happens if we get a lot of polar compounds together. So I'm trying to set you up with a good foundation of understanding polar compounds. A polar covalent bond gives you a polar compound, and that means one end is a little positive, one end is a little negative. Not a full out positive and negative like ionic, but partial. So we use this sigma little symbol, Greek symbol, to tell each other, to tell one chemist to another, that it's a partial charge. Okay, now we're ready for that last column in your notes, the one on the far right. Metallic bonds will form, right, between metals. Now what this means is, depending on the metals, we could have a very large or very small difference in electronegativities. It can vary a lot, but it's still going to be metals. And so, I know, you're awed by my artistic ability. Anytime we're like only on this side of the stair-step line, let's call that metallic bonding. That's a really great kind of generalization there. Okay, so metallic bonds will vary widely in characteristics. It will depend very much on exactly what elements you're looking at that very moment. And we'll be carrying that theme throughout the rest of the notes. Okay, so that was topic 2. You draw your line, okay? And so we had row 1 was composition of the bond, row 2 was elements involved. We're going to stop this video here. We'll pick up with topic 3, the next one, on the very next video. But this way, if you know which day you missed, you can fill in the gaps easy by not watching a whole huge hour-and-a-half long video. And it also helps with download speeds and all that sort of thing. So next video, we're going to start with topic 3. Again, this was video number 2, and we took care of topics 1 and 2. Good luck.